Iridium is a chemical element with symbol Ir and atomic number 77. A very hard, brittle, silvery-white transition metal of the platinum group. Iridium is generally credited with being the second densest element based on measured density, although calculations involving the space lattices of the elements show that iridium is denser. It is also the most corrosion-resistant metal, even at temperatures as high as 2000 degrees Celsius. Although only certain molten salts and halogens are corrosive to solid iridium, finely divided iridium dust is much more reactive and can be flammable. Iridium was discovered in 1803 among insoluble impurities in natural platinum. Smithson Tennant, the primary discoverer, named iridium for the Greek goddess Iris, personification of the rainbow, because of the striking and diverse colors of its salts. Iridium is one of the rarest elements in Earth's crust, with annual production and consumption of only 3 tons. 191 Ir and 193 Ir are the only two naturally occurring isotopes of iridium, as well as the only stable isotopes. The latter is the more abundant of the two. The most important iridium compounds in use are the salts and acids it forms with chlorine, though iridium also forms a number of organometallic compounds used in industrial catalysis and in research. Iridium metal is employed when high corrosion resistance at high temperatures is needed, as in high-performance spark plugs, crucibles for recrystallization of semiconductors at high temperatures, and electrodes for the production of chlorine in the chlor-alkali process. Iridium radioisotopes are used in some radioisotope thermoelectric generators. Iridium is found in meteorites with an abundance much higher than its average abundance in Earth's crust. For this reason, the unusually high abundance of iridium in the clay layer at the Cretaceous-Paleogene boundary gave rise to the Alvarez hypothesis that the impact of a massive extraterrestrial object caused the extinction of dinosaurs and many other species 66 million years ago. It is thought that the total amount of iridium in the planet Earth is much higher than that observed in crustal rocks. But as with other platinum group metals, the high density and tendency of iridium to bond with iron caused most iridium to descend below the crust when the planet was young and still molten. Characteristics. Physical properties. A member of the platinum group metals, iridium is white, resembling platinum, but with a slight yellowish cast. Because of its hardness, brittleness, and very high melting point, solid iridium is difficult to machine, form, or work. Thus powder metallurgy is commonly employed. Instead, it is the only metal to maintain good mechanical properties in air at temperatures above 1600 degrees Celsius. It has the 10th highest boiling point among all elements and becomes a superconductor at temperatures below 0.14 K. Iridium's modulus of elasticity is the second highest among the metals, only being surpassed by osmium. This, together with a high shear modulus and a very low figure for Poisson's ratio, indicate the high degree of stiffness and resistance to deformation that have rendered its fabrication into useful components a matter of great difficulty. Despite these limitations and iridium's high cost, a number of applications have developed where mechanical strength is an essential factor in some of the extremely severe conditions encountered in modern technology. The measured density of iridium is only slightly lower than that of osmium, the densest element known. Some ambiguity occurred regarding which of the two elements was denser, due to the small size of the difference in density and difficulties in measuring it accurately, but with increased accuracy in factors used for calculating density, X-ray crystallographic data yielded densities of 22.56 grams per cc for iridium and 22.59 grams per cc for osmium. Chemical properties. Iridium is the most corrosion-resistant metal known. It is not attacked by almost any acid, aqua regia, molten metals, or silicates at high temperatures. It can, however, be attacked by some molten salts, such as sodium cyanide and potassium cyanide, as well as oxygen and the halogens at higher temperatures. compounds. Iridium forms compounds in oxidation states between -3 and +9. The most common oxidation states are +3 and +4. Well-characterized examples of the high +6 oxidation state are rare, but include IRF6 and 2 mixed oxide Sa2M gyro 6 and senior 2 Cairo 6. In addition, it was reported in 2009 that iridium oxide was prepared under matrix isolation conditions by UV irradiation of an iridium peroxide complex. This species, however, is not expected to be stable as a bulk solid at higher temperatures. The highest oxidation state, which is also the highest recorded for any element, is only known in one cation, IRO+4. It is only known as gas phase species and is not known to form any salts. Iridium dioxide, IRO2, a brown powder, is the only well-characterized oxide of iridium. A sesquioxide, IR203, has been described as a blue-black powder which is oxidized to IRO2 by HNO3. The corresponding disulfides, diselenides, sesquisulfides, and sesquiselenides are known, and IRS3 has also been reported. Iridium also forms iridates with oxidation states +4 and +5, such as K2IRO3 and KIRO3, which can be prepared from the reaction of potassium oxide or potassium superoxide with iridium at high temperatures. Although no binary hydrides of iridium IRXHY are known, complexes are known that contain IRH4-5 and IRH3-6, where iridium has the +1 and +3 oxidation states, respectively. The ternary hydride Mg6Ir2H11 is believed to contain both the IRH4-5 and the 18-electron IRH5-4 anion. No monohalides or dihalides are known, whereas trihalides, IRX3, are known for all of the halogens. For oxidation states +4 and above, only the tetrafluoride, pentafluoride and hexafluoride are known. Iridium hexafluoride, IRF6, is a volatile and highly reactive yellow solid, composed of octahedral molecules. It decomposes in water and is reduced to IRF4, a crystalline solid, by iridium black. Iridium pentafluoride has similar properties, but it is actually a tetramer, IR4F20, formed by 4 corner-sharing octahedra. Iridium metal dissolves in molten alkali metal cyanides to produce the IR3+6 ion. Hexachlorouridic acid, H2IRCl6, and its ammonium salt are the most important iridium compounds from an industrial perspective. They are involved in the purification of iridium and used as precursors for most other iridium compounds, as well as in the preparation of anode coatings. The IRCl2-6 ion has an intense dark brown color, and can be readily reduced to the lighter colored IRCl3-6 and vice versa. Iridium trichloride, IRCl3, which can be obtained in anhydrous form from direct oxidation of iridium powder by chlorine at 650 degrees Celsius. Or in hydrated form by dissolving IR2O3 in hydrochloric acid, is often used as a starting material for the synthesis of other IR compounds. Another compound used as a starting material is ammonium hexachloroiridate, 3-IRCl6. Iridium complexes are diamagnetic and generally have an octahedral molecular geometry. Organoiridium compounds contain iridium carbon bonds where the metal is usually in lower oxidation states. For example, oxidation state 0 is found in tetrairidium dodecacarbonyl, IR412, which is the most common and stable binary carbonyl of iridium. In this compound, each of the iridium atoms is bonded to the other 3, forming a tetrahedral cluster. Some organometallic IR compounds are notable enough to be named after their discoverers. One is Vasquez complex, IRCl-P3, which has the unusual property of binding to the dioxygen molecule, O2. Another one is Crabtree's catalyst, a homogeneous catalyst for hydrogenation reactions. These compounds are both square-planar, D8 complexes, with a total of 16 valence electrons, which accounts for their reactivity. An iridium-based organic lead material has been documented, and found to be much brighter than DPA or PPV, so could be the basis for flexible OLED lighting in the future. Isotopes. Iridium has two naturally occurring, stable isotopes, 191 IR and 193 IR, with natural abundances of 37.3% and 62.7%, respectively. At least 34 radioisotopes have also been synthesized, ranging in mass number from 164 to 199. 192 IR, which falls between the two stable isotopes, is the most stable radioisotope, with a half-life of 73.827 days, and finds application in brachytherapy and in industrial radiography, particularly for non-destructive testing of welds in steel in the oil and gas industries. Iridium-192 sources have been involved in a number of radiological accidents. Three other isotopes have half-lives of at least a day: 188 IR, 189 IR, and 190 IR. Isotopes with masses below 191 decay by some combination of beta plus decay, alpha decay, and proton emission, with the exceptions of 189 IR, which decays by electron capture. Synthetic isotopes heavier than 191 decay by beta minus decay, although 192 IR also has a minor electron capture decay path. All known isotopes of iridium were discovered between 1934 and 2001. The most recent is 171 IR. At least 32 metastable isomers have been characterized, ranging in mass number from 164 to 197. The most stable of these is 192 square meters IR, which decays by isomeric transition with a half-life of 241 years, making it more stable than any of iridium's synthetic isotopes in their ground states. The least stable isomer is 190 cubic meters IR with a half-life of only 2 microseconds. The isotope 191 IR was the first one of any element to be shown to present a Mssbauer effect. This renders it useful for Mssbauer spectroscopy for research in physics, chemistry, biochemistry, metallurgy, and mineralogy. History. The discovery of iridium is intertwined with that of platinum and the other metals of the platinum group. Native platinum used by ancient Ethiopians and by South American cultures always contained a small amount of the other platinum group metals, including iridium. Platinum reached Europe as platina, found in the 17th century by the Spanish conquerors in a region today known as the Department of Choco in Colombia. The discovery that this metal was not an alloy of known elements, but instead a distinct new element, did not occur until 1748. Chemists who studied platinum dissolved it in aqua regia to create soluble salts. They always observed a small amount of a dark, insoluble residue. Joseph Louis Proust thought that the residue was graphite. The French chemists Victor Collet Descartes, Antoine-François Comte de Fourcroy, and Louis-Nicolas Vauquelin also observed the black residue in 1803, but did not obtain enough for further experiments. In 1803, British scientist Smithson Tennant analyzed the insoluble residue and concluded that it must contain a new metal. Vauquelin treated the powder alternately with alkali acids and obtained a volatile new oxide, which he believed to be of this new metal, which he named tenor, from the Greek word pi tau eta nu omicron sigma tennis, winged. Tennant, who had the advantage of a much greater amount of residue, continued his research and identified the two previously undiscovered elements in the black residue, iridium and osmium. He obtained dark red crystals by a sequence of reactions with sodium hydroxide and hydrochloric acid. He named iridium after Iris, the Greek winged goddess of the rainbow and the messenger of the Olympian gods, because many of the salts he obtained were strongly colored. Discovery of the new elements was documented in a letter to the Royal Society on June 21, 1804. British scientist John George Children was the first to melt a sample of iridium in 1813 with the aid of the greatest galvanic battery that has ever been constructed. The first to obtain high-purity iridium was Robert Hare in 1842. He found it had a density of around 21.8 grams per cc and noted the metal is nearly malleable and very hard. The first melting in appreciable quantity was done by Henri St. Clair de Ville and Jules Henry Debray in 1860. They required burning more than 300 L of pure O2 and H2 for each kilogram of iridium. These extreme difficulties in melting the metal limited the possibilities for handling iridium. John Isaac Hawkins was looking to obtain the fine and hard point for fountain pen nibs, and in 1834 managed to create an iridium-pointed gold pen. In 1880, John Holland and William Lowfland Dudley were able to melt iridium by adding phosphorus and patented the process in the United States. British company Johnson Matthey later stated they had been using a similar process since 1837 and had already presented fused iridium at a number of world fairs. The first use of an alloy of iridium with ruthenium in thermocouples was made by Otto Fusner in 1933. These allowed for the measurement of high temperatures in air up to 2000 degrees Celsius. In Munich, Germany in 1957, Rudolf Mssbauer, in what has been called one of the landmark experiments in 20th century physics, discovered the resonant and recoil-free emission and absorption of gamma rays by atoms in a solid metal sample containing only 191 IR. This phenomenon, known as the Mssbauer effect, and developed as Mssbauer spectroscopy, has made important contributions to research in physics, chemistry, biochemistry, metallurgy, and mineralogy. Mssbauer received the Nobel Prize in Physics in 1961, at the age 32, just 3 years after he published his discovery. In 1986, Rudolf Mssbauer was honored for his achievements with the Albert Einstein Medal and the Elliott Cresson Medal. Occurrence. Iridium is one of the 9 least abundant stable elements in Earth's crust, having an average mass fraction of 0.001 ppm in crustal rock. Gold is 40 times more abundant, platinum is 10 times more abundant, and silver and mercury are 80 times more abundant. Tellurium is about as abundant as iridium. In contrast to its low abundance in crustal rock, iridium is relatively common in meteorites, with concentrations of 0.5 ppm or more. The overall concentration of iridium on Earth is thought to be much higher than what is observed in crustal rocks. But because of the density and hydrophilic character of iridium, it descended below the crust and into Earth's core when the planet was still molten. Iridium is found in nature as an uncombined element or in natural alloys, especially the iridium-osmium alloys, osmiridium, and iridosmium. In the nickel and copper deposits, the platinum group metals occur as sulfides, tellurides, antimonides, and arsenides. In all of these compounds, platinum is exchanged by a small amount of iridium and osmium. As with all of the platinum group metals, iridium can be found naturally in alloys with raw nickel or raw copper. Within Earth's crust, iridium is found at highest concentrations in 3 types of geologic structure: igneous deposits, impact craters, and deposits reworked from one of the former structures. The largest known primary reserves are in the Bushveld igneous complex in South Africa, though the large copper-nickel deposits near Norilsk in Russia, and the Sudbury Basin in Canada are also significant sources of iridium. Smaller reserves are found in the United States. Iridium is also found in secondary deposits, combined with platinum and other platinum group metals in alluvial deposits. The alluvial deposits used by pre-Columbian people in the Choco Department of Colombia are still a source for platinum group metals. As of 2003, the world reserves had not been estimated. Cretaceous-Paleogene boundary presents the Cretaceous-Paleogene boundary of 66 million years ago, marking the temporal border between the Cretaceous and Paleogene periods of geological time, was identified by a thin stratum of iridium-rich clay. A team led by Luis Alvarez proposed in 1980 an extraterrestrial origin for this iridium, attributing it to an asteroid or comet impact. Their theory, known as the Alvarez hypothesis, is now widely accepted to explain the extinction of the non-avian dinosaurs. Dewey M. McLean and others argue that the iridium may have been of volcanic origin instead, because Earth's core is rich in iridium, and active volcanoes such as Piton de la Fournaise, in the island of Reykjavik Union, are still releasing iridium. Production. Iridium is also obtained commercially as a byproduct from nickel and copper mining and processing. During electro-refining of copper and nickel, noble metals such as silver, gold and the platinum group metals as well as selenium and tellurium settle to the bottom of the cell as anode mud, which forms the starting point for their extraction. To separate the metals, they must first be brought into solution. Several separation methods are available depending on the nature of the mixture. Two representative methods are fusion with sodium peroxide followed by dissolution in aqua regia, and dissolution in a mixture of chlorine with hydrochloric acid. After the mixture is dissolved, iridium is separated from the other platinum group metals by precipitating ammonium hexachloroiridate to IRCl6, or by extracting IRCl2-6 with organic amines. The first method is similar to the procedure Tennant and Wollaston used for their separation. The second method can be planned as continuous liquid-liquid extraction and is therefore more suitable for industrial-scale production. In either case, the product is reduced using hydrogen, yielding the metal as a powder or sponge that can be treated using powder metallurgy techniques. Iridium prices have fluctuated over a considerable range. With a relatively small volume in the world market, the iridium price reacts strongly to instabilities in production, demand, speculation, hoarding, and politics in the producing countries. As a substance with rare properties, its price has been particularly influenced by changes in modern technology. The gradual decrease between 2001 and 2003 has been related to an oversupply of IR crucibles used for industrial growth of large single crystals. Likewise, the prices above $1,000 Oz between 2010 and 2014 have been explained with the installation of production facilities for single crystal sapphire used in LED backlights for TVs.